Welcome back, everybody. In the previous lecture, we talked about understanding wireless theory, right? The carrier signal, the wave, the frequency, all that good stuff. Now, in this particular lecture that we're going to get into is the intelligence, the modulation. And there's three main types of modulation we will discuss, which is frequency, hopping, spread spectrum. There's DSSS, direct sequence spread spectrum, and OFDM, which is orthogonal frequency division multiplexing. Okay, so and I'll get into it in the lecture, but just to give you a heads up before we get into the lecture, there's going to be a lot of terminology that you're going to be like, what is he saying? All right, like PSK, which is phase shift keying. All right, and remember, these are terminologies that are going to help you in your certification. When you're creating a wireless network, obviously you have your spectrum analyzers and all this good stuff that you're going to look at doing your radio site survey, physical site survey, where to place the APs and all that good stuff. But for testing purposes, yeah, look at the terminology that we're going to be going over. Very important. Understanding, all right, what modulation is, which is basically just putting how the data gets put onto these carrier waves and how they get manipulated, the waves, they get manipulated based on the type of modulation, all right? So enough said. There's enough talking in the actual lecture. So let's get with it. So I'll see you in the lecture. All righty, welcome everybody. This is gonna be a long lecture, like I said. So get comfortable, because in the previous, like I said earlier, in the previous lecture, we started to understand what the carrier signal is and how it's created and how far it goes, or how much clearer it would be depending on the frequency and not the modulation, or the amplitude, right? Because you got the frequency, the amplitude, the phase, all right? All those things determine how far is it going to be interfered with. If not, between, let's say, 2.4 and 5 gigahertz, we made that comparison and where they lie. Here, what we're going to be talking about is different types of modulation. This is the intelligence that we put onto that carrier wave. And it will be different from standard to standard to standard. And we're using the latest standards of today. We'll discuss it, obviously, in this particular lecture. It is something called OFDM, and we'll get into it when we get there. Okay, but there are different types of modulation. And again, all that is where the carrier signal is modulated or changed according to some source, some other source. Like you have the standard that you're using, and you have this carrier wave. So the carrier wave, the modulation, the intelligence that is putting inside that wave is going to shift at certain lengths, okay? It may be compressed, it may be longer, wider, right? Because it sends it one way, and then on the other side, it demodulates it so it can understand it, all right? It will separate it again, and that will be, it's very true, and that's why OFDM is the one we use today on how that particular works. But RF modulation, like I say, has a predefined rate that it goes at. When we talk about different types of data rate, all right? It's funny, that wording right there, reasonably immune to interference. It all depends, again, on so many things. That's why wireless is not like wired at all. Wired, as long as you keep it, if you have Cat 6, that plastic thing, everything is twisted, you keep it away, high voltage, you should be good to go. The only thing you need to be worried with is attenuation, right? Well, in wireless, not only do you need to be concerned with attenuation because of how far the signal is going, right, from the AP to the end device or what have you, all right, that's why we have that 15% overlap. But now we also need to make sure that we don't have cold channel interference and all these different things. So the modulation type has to do with that as well. All right, so the better the modulation, the better a way that it treats that wireless signal, and it could separate them better, and as that when you're going from peak to peak, it will be either closer or further apart. That will definitely make a huge difference as far as interference. All right, so again, there's different ones, and it says here, interprets the added information based on the changes in the carrier signal. That's when it's talking about the changes, is the peaks, right, that it creates. Remember that one complete cycle is going all the way to the top, then coming all the way to the bottom, and coming back up to the center, right? That's what that wavelength is. Now, Due to the physical properties of our signal, we talked about frequency, but only by varying slightly above or below the carrier frequency. So we have the frequency, the phase, and the amplitude. We talked about that. All right, and we normally work with right now 2.4 gigahertz and 5 gigahertz. All right, we saw that 2.4 gigahertz can travel further, has a larger amplitude. Okay, so it'll travel further, but a lot of things interfere with it because of the frequency that it's in. It has a bigger amplitude. The phase, depending on the standard you're using, it could be 22 megahertz. Okay, big, or depending, on what you're using, it could be smaller, like 5 gigahertz. Okay, it's more frequent, but the amplitude is less. But in the 5 gigahertz and the 2.4, they use different types of modulation. They use different types of modulation where what it does to that signal that's on that carrier wave in order to send the information clearer and have less interference as it's going out. Not only that, what people don't understand is also that if there's somebody out there actually trying to sniff out information on the wireless wave, which is easily done, you'll only get part of it because it actually breaks up the data that's going through there, okay, into 4 bits, 8 bits. I mean, it just, the signal that's on that carrier wave is chopped up, all right, and then it's scrambled up, and then once it gets to the other side, it puts it back together. That's why it says that the receiver is different. The change is from sender to receiver. Okay, so it's modulated and demodulated. So it's kind of encrypted and then unencrypted. Think of it that way. Now, the very beginnings of modulation started with what you see there, FHSS, which is frequency hopping spread spectrum. And this, just a little history, started with in the military. The men and women, the armed forces, right? They could try and communicate out there in the middle of nowhere. They change the frequency they emit on the radio every so many after, let's say, 12 hours. They change the frequency, and everybody knows already a predetermined frequency they need to be on every day or what have you. Okay, so they can't get caught. So it's frequency hopping. It goes from one frequency to the other, to the other, to the other. And then in the beginning stages of wireless, this is something that we used, okay, frequency hopping spectrum, but it wasn't that wasn't the best in the world, all right? So then came, let's see here, figures that we'll talk about it when we get there. Frequency hopping spectrum, the wireless band was divided to 79 channels. Look at that, 79 channels or fewer, with each channel being 1 megahertz wide. Well, that's an issue. That's an issue, being 1 megahertz wide. And to avoid interference, as I mentioned, we need to continuously hop between frequency across all bands. So imagine a channel that's only 1 megahertz wide. They're pretty tight in there. And to avoid the interference, I said that the actual transmission would hop from one frequency to another to avoid, colliding with the other channel. Okay, so that's an issue. So that's why they call it frequency hopping, and that was a big problem. You look at it here, okay? If you look at it, and this is interesting, he said the frequency range is divided into channels, right? And you see all the different channels here, okay? And the data is transmitted on these randomly ordered channels. But again, they're so close to each other. You see the differences in peaks. Remember, that's the phase. So you see here that's only 1 megahertz wide. Well, that's an issue. That's an issue due to the fact that they have to go through different frequencies in order not to interfere with each other. That's where the big problem with using this type of modulation became, okay? And so we replaced that using DSSS, okay? Narrow, 1 megahertz channel, data rate of 1 or 2 megabits per second. We're talking about the original standard of 802.11. Not 11A or 11B, no, 802.11, period. All right. Then we came up with 802.11B, then A, then we went to G, then we went to N, and now we're in A. Well, now we've been using AC, and now we have AX, right? So, and again, AX uses the latest and greatest. All right. So does AC, which is OFDM. So FH, frequency hopping spread spectrum, it's frequency hopping spread spectrum. So that was a typo right there. I know. Okay, don't freak out. That's an S. Frequency hopping spread. That has been a mistake there. Spectrum was replaced by DSSS, okay? And we'll talk about DSSS right now. So it's direct sequence spread spectrum, DSSS. So what it does, it already has a fixed number of wide channels, and it's 22 megahertz wide. So it's a lot better, right? And it works in the 2.4 gigahertz band. But even though you see there's 14 possible channels, only 3 of them, and we know this, we talked about this previously, in the 2.4 gigahertz band, we can only use channels 1, 6, and 11. And I believe the default is 1. All right, and that's the problem that people don't understand. When you buy these devices, they come with default settings. All right, if you're buying it for a home use, people don't really pay attention, especially if it's an end user. Not everybody's in IT. Okay, it's an end user. Grandma, grandpa, aunt, uncle, whatever the case may be. They really don't understand. They sell them an item. So hey, you can go online right away, or you just plug it into a wall, plug it into your whatever, and you're good to go, right? You start just, they do no security on there, they don't change anything, whatever. They don't understand about channels. But we do in IT. We need to understand that 2.4 gigahertz has only 3 channels that don't overlap. That's extremely important. Now, we're using a better modulation. Okay, that's all right, it's great. It's using a number of fixed wide channels that can support complex modulation. That means what it does to the actual wavelength. All right, for it to change. All right, so it doesn't have to hop through a million different frequencies. All right, so it's a lot better. It's a lot wider channel. So it's not going to have a lot of co-channel interference, which is great. All right, but again, you only have 3 channels. You only have 3 channels. Wireless transmitters perform several functions to make data stream less susceptible to being degraded along its path. Now, that last bullet point right there. Wireless transmitters. This is where your wireless repeaters come in as well. All right. Depending on what kind of, and again, we've talked about the wireless devices, routers, all-in-one routers, wireless controllers, wireless APs, wireless repeaters, wireless bridges. Okay. So it all depends what you're using. Because if you're going from on a home like I'm in right now, okay, my all-in-one router is downstairs. I have a wireless repeater, not that I need it, but I have a wireless repeater upstairs. It just makes the signal a lot better, And I have the capability of running that full 802.11 AC of 1 gigabit per second, okay? Because my internet has 1 gigabit per second, and my wireless running 802.11 AC has that 1 gigabit capability. I'm almost at that speed, which is awesome, internally and externally. All right, so these are things you need to think of, not just, the wireless transmitters perform several functions to make data stream less accessible. No. You need to think about what you're doing, okay? What devices are, that's why, and I'm going to repeat this throughout this entire course, is the spectrum. You need to do your radio frequency site survey. Your radio, not only your physical site survey, but your radio frequency site survey. You need to see where there's interference, where there's dead zones, where you're going to place these APs. Now, some laptops comes ready with software installed that you can use it. If you don't you want to get a spectrum analyzer, all right, that's fine. All right, I don't care how you do it, but make sure that you're placing these APs where they're going to overlap. And if you don't, you're just going to wing it. Okay, make sure that you walk around with your laptop like I used to do in schools to teach students. I would walk around with the laptops and we were like, okay, we got signal, we don't got signal. Oh, well, I can still print, I can't still print. We'll walk out into the parking lot and do all these things. You need to check. So it's a combination of different things in wireless. Because remember, we haven't talked about actual, antenna types. We haven't talked about the interference, the different types of interference that you get with wireless. We haven't dived into that, but we will. All right, that you're going to get in a wireless network. That you're going to get in a wireless network because it's insane. It's insane. Air, drywall, steel, glass, wood, your body. All right, everything interferes with wireless. Not to mention, if you have, if you're running 2.4 and you have your router, like I've said before, right next to your TV. Yeah, that's not doing you any good. All right, you have a lot of EMI and RFI interference that's going to just kill your signal. All right, so that's why you have repeaters, and there's all sorts of repeaters. I've bought crappy repeaters that just those antennas that you plug into the power, and they supposedly increase your signal. Yeah, they're crap. Okay, that one's that I bought anyway. But there's a million repeaters. Do your research before you purchase anything. But it's when you're doing a wireless network, ladies and gentlemen, definitely by today's standards, if anybody's running anything less than 802.11g, I'm sorry. Okay, I really am. That's the lowest you should go. 2.4 gigahertz. If you analyze your network and you look at the speeds that you're running at internally, and you're running at 1 megabit per second, yeah, there's an issue. There's an issue. There's a lot of interference. The APs are too far apart. Whatever the case may be. So when they say wireless transmitters, you need to go in there and see what's going on. If it's just a blank slate, they just have a wired network and they want you to make a wireless, well then, perfect. You do it right from the get-go. All right, but it is important. And here you see the direct sequence spectrum. What it does, it gets the data, it scrambles it. Oh my God, I can't say that word. It scrambles it up into different digital signals, right? Chopped up. It goes into a particular coder that turns it into a symbol. And then before it goes then into an interleaver, okay? Because you see here it says here chip, 11 megahertz chipping rate. All right, that's what it's doing in the coder. Then it interleaves that and goes to the modulator, and then it demodulates the signal or it modulates the signal and sends it out the antenna, right? And it sends it out. When we get to the other side, then it demodulates. It goes in the opposite direction. It's like the OSI model, encapsulation and de-encapsulation, modulation, demodulation. Okay, same thing. But this is what DSSS, okay, does. All right, that was hard to say. But it does a very good job, all right, better than FHSS, frequency hopping spread spectrum, where it has 76 different channels, only 1 megahertz wide. It's got to go through 76 different frequencies to send the information so it doesn't interfere with each other. Well, here we don't have that. We have a 22 megahertz, okay? And here it says 11, but again, it all depends the type of phase shift keying that you're doing. Okay, but obviously DSSS is what we use today. All right, and this is one of the things. And this is what I mean by phase shift keying. Okay, you have 1 megabit data rates. All right, to minimize the effect of the signal to noise ratio, and data loss due to narrow band. I want to emphasize something. Pay attention. Narrow band interference. Individual bits of data are encoded in a sequence of 11 bits called, this is what they just call Barker 11 code. All right, no big deal. So we have less signal to noise ratio. That makes sense, right? Okay. So basically adds more information to maintain the integrity of the data. Okay. There are only two possible values in Barker chips, 0 and 1. Well, damn. Okay. So that's what's called right here. You see it down here? DBPSK. PSK stands for phase shift keying. Oh, here it is. Binary phase shift keying or differential binary phase shift keying. Now, before you start freaking out, okay, are they going to ask you stuff like this in the certification? If they do, sorry, okay? But these are things you need to understand. And really, when you're setting up a wireless network, I mean, as long as you do your surveys, physical and radio, and you have the right APs and you place them in the right place, and you just configure your stuff, you ain't going to be messing around with none of this, okay? It's going to run it on its own, all right? So you don't have to go in there and, well, I'm running DBP. No. Yeah, you don't. No. So just understand what it's doing, all right? And we're going to get a visual in a second. You see that it says, well, 0 data bit, that's the binary, what it looks like. If it's a 1 data bit, that's what the binary looks like. They're not going to ask you that, but just so you know, all right? And you see here, the phase is not changed. If there's a 0, the phase is not changed. If the phase is rotated 180 degrees, then it goes to 1. And again, that is binary, differential binary phase shift keying. Okay. On the other hand, all right, you have 2 megabits per second data rate. Now here we use something. I know you're gonna freak out. Differential. I know I did when I first heard it. Quadrature phase shift keying. So it actually gives you 2 megabits data rate, and what it's doing, if it sees, is it puts 2. It's instead of using just zeros and ones, it uses 2 zeros, and then 0 or 0 1, it uses 2 bits. Okay, so if it's 0 0, no change. If it's a 0 1, okay, it's 90. Oh, it's a 1 1. Oh, it's a 180. Oh, if it's a 1 0, well, that makes sense, right? It's increasing. So 270. So that is differential quadrature. Here it is. Again, terminology. But this is what DSSS does. Okay, my God. All right, but also OFDM does this as well in higher rates. All right, because you have higher types of differential quadrature higher. All right, which it makes the phase is going to go through different phases to give you more ways to modulate the signal and get and that's what they did with Wi-Fi 6. It's not that they're putting more power through it. It's not that it's still 5 gigahertz, but you're going to get a clearer signal, a more crisp signal, you can send more information or on that carrier wave because of the type of modulation and the type of quadrature or phase shift keying, okay, that is using, all right, that's the key there in Wi-Fi 6, all right, in the actual modulation, okay, the PSK, I'm not going to say that word again, all right, the PSK, what it's doing with that is what makes Wi-Fi 6 faster, okay, and it makes it more crisper, all right, and clearer for when you get the information, and less interference, obviously. But it's still 5 gigahertz. It's still in the 5 gigahertz channel, all right, or frequency, I'm sorry, 5 gigahertz frequency. So, again, you still have those 23 non-overlapping channels, you still have all these different things, but again, their phase shift keying is different. It's different. And here you can take a look at the binary. Here's what it means, okay? Remember we said 1, it changes. So we got 1, okay, because it changed here. You see, it changed 1. Here, no change, right? 0, 0, 0 change, 1, right? Got to change, 1, change, 1, yeah, no change, 0, stays the same. Here, it's 2, all right? And that's where the difference comes in. And again, all this, that T is time. Everything is measured in time, okay? So if there's a change, then it'll shift it, depending. Remember this one was, what was this one? I forgot. 180 degrees, okay? So it's a 180 degree turn, okay? It'll change. Here's a 270 degrees. Here's, I believe it was, 90 degrees, okay? So again, it's something you memorize for a test, just in case they ask. But know that when we started with DSSS, I'm actually counting on my fingers, DSSS, all right? We started with this type of PSK or phase shift keying, okay? So we can send the signal much better. So we can add more intelligence to that carrier wave, modulate that carrier wave, okay? Scramble things up, all right? So we can send more information. That's what they're doing. And they won't interfere with each other because between peaks, you have the larger channel, right? The larger phase. All right. So in the 5 megabit and the 5.5 megabits data rate, it's like, whoa! Now we have something called CCK, right? Complementary code keying terminology. That's it. CCK. All right. So now I can do 4 bits of data at a time. But now I create, remember when we looked at that visual? Remember here? Right here, that says symbol. This chip, it's encoding and it turns it into a symbol. Okay. So here is 4 bits of data at a time instead of 1 or 2. Here, that's 4 bits at a time, which creates a unique 8-chip symbol. Now it's a 1.375 megahertz, so 8 data bits per symbol, resulting in 11. It's still 11 megabits per second. Think about it. We can run 802.11a, which is an older standard, okay? And we can run a 5 gigahertz. 54 megabits per second. 54 megabits per second. That's 11. And we're talking about some crazy stuff now where, CCK using, creating 5.5 megabits per second data rate. So it creates this unique symbol. So when the modulation, it just separates it into 8 data bits per symbol. It's like MPLS puts everything in a label, but here it puts everything in a symbol. Okay, so now, and that symbol, no, we don't have 1 or 2 or 4, we have 8 data bits. And we only get 11 megabits per second. So imagine what happens if we want to use, 802.11ac at 1 gigabit per second internally. Now remember, we're talking about internal wireless LANs, that your one PC is communicating to another PC. If it's one floor within whatever floor, you're communicating with a printer or in your home, whatever the case may be. We're not going across wide area networks. We're talking about wireless LANs, okay, wireless local area networks. All right, so that's just internal. Don't start thinking, well, my internet provider. No, that's another story altogether. Okay, we're talking about internally. What's your speed internally? And that's what people have a confusion with when they're setting up wired or wireless networks. Because people at home, they have, let's say, home businesses or small offices or whatever, they run it from their house. That's perfectly fine. Let's just talk about the house. They say, man, my internet's so slow. This wireless sucks. What the hell does your wireless got to do with the internet signal? Okay? Whatever you purchased from an ISP is what you got. That's it. Now, if let's say like me, I through my ISP, I have the capability of going a gig, right? And I'm running 802, 2.4 gigahertz, okay, 802.11, G, okay, and I'm only getting 11 meg. Well, that's my own fault. That's my bottleneck right there. I'm so slow internally. I'm so slow trying to get to that router. Okay, that's your problem. But I match up everything. So if I got 1 gigahertz going out to the internet, or one gigabit per second, and I got AC that gives me 1 gigabit wirelessly internally, that means that I can print, I can share folders, I can get into other computers at that rate. Okay, don't blame your internet speed on your wireless internally. Now, if you're running 11 megabits per second internally, and you have friggin', an OC, 150 or whatever, 151, OC 152, okay, an optical fiber line going out, you have 10 gigabits per second, whatever, Metro E, whatever it is that you have, and you still think, man, I'm slow. You're slow because getting to the router is slow. And that's what you need to look at. There's two things you need to look at: your local area network and your wide area network, because you can do a speed test and they always do that to you, don't they? Your ISP. When you do a speed test, they make you plug into your router. Plug into your router. And then you do a speed test and you're hauling ass. When you get to you try to test it wirelessly, you're like, man, it's so slow. Slow because you're getting to it, you're slowing it down to begin with. You're the bottleneck, not your ISP. All right? Because do it at the same time, all right, and you'll see. But I never do that. When they tell me you plugged in, I'll go, yeah, no, I'm not. Okay? So it's no. So you don't. That's one thing in wireless that they tell you. They used to tell you. They don't tell you anymore. Why, I don't know. Is that you shouldn't be mixing and matching different vendors. If you're using one standard, make sure you use the same standard across the whole thing. All right. Don't be mixing 802.11g with 802.11n, 802.11ac. It's like, what are you doing? What are you doing? You have an 802.11ax router, and you have NIC cards on your laptops or desktops or whatever wireless devices you have, and devices that can only support 11 megabits per second. Oh, that's brilliant. Okay, so you gotta make sure that everything matches up. Okay, because that's the same thing in a wired network. Think about it. You have a 10 megabit per second NIC card, and you're plugging it into a switch that supports gigabit, but you're not gonna get that. Anybody that's been in the field knows that those little lights turn on, and that's the speed you're going at. If you ever had a firewall, it'll tell you it's going at 10 megabits per second, 100 megabits per second, 1 gigabit per second, depending on the type of cabling you're using. Okay, so don't do that. It's like getting gigabit. You got a gigabit switch, gigabit router capability. You have 10 gigs in your internet, and you're running Cat5. What are you doing? What are you doing? No. If everything's a gig, then your NIC should be gigs, your cable should be Cat6, should be Cat. Well, as Cat5 Big E supports a gigabit the first 250 feet. No. Cat6 is what you need to be running. Same thing with wireless. With wireless, even more so. Don't mix and match standards. Okay, if you're running 802.11 AC, everything should be, what it supports, which is, gigabit. All right, so make sure you have that. All right, and don't be buying, I don't know, Linksys and then buy a Netgear or buy a Fortinet and then something else. I mean, you need to try to maintain some sort of same type of vendor, consistency in your networking devices, because each vendor will work a little differently. So, and with wireless, as it is, everything interferes with it. You don't want your devices messing that up as well. All right. Now I get into, and first time I saw this word, I'm like, what the heck? Orthogonal, which is what we use today. Orthogonal frequency division multiplexing. What the hell does that mean? It means two or more objects act independently, they don't depend on each other or interfere with other signals. Okay? It works by splitting the radio signal into multiple smaller subsignals and then transmit it simultaneously at different frequencies to the receiver. So it creates different frequencies, and it's done again by the PSK, right? Phase shift keying, the way it does that. So definitely orthogonal, it will be the way to go, and that's the way you go now. If you have AC, if you have WiMAX, if you're using 3G, 802.11 AC and higher are going to use OFDM. Okay, and the higher you go, like now with Wi-Fi 6, you're going to be using a different type of phase shift keying. If you look at it, let me explain what I mean about that. Here is OFDM. All right, so you have, let's look at the different colors. You have purple, red, blue, green. I think this is great. Okay, and then it's going to send a signal here, but here we have like a little gap. You see how when this is doing something at this peak, because remember, from peak to peak, that's the phase. So from peak, when this is peaking, let's say it's at 1, this is at 0 down here. They're all the other ones are down here. When this is at the peak, everybody else is down here. The red, the blue, the green, they're all down here. The gray, they're all down here. When this is peaking, right, then the purple, the blue, the green is at 0, nothing. So when they're at their peak, the other frequencies are at the bottom. So they're not going to be interfering with that one. So that's why it's going to be a lot crisper. So their phase shift keying is completely different, and a lot, it has a more wider range that you can put more intelligence on it. Okay, and it's based on that, quadrature. Remember how I created a symbol? Now, well, this is the same thing. Okay, it's the same thing. So, but that's what it does. So it takes all these different frequencies and they can be compressed because it compresses them. Okay, but it puts something in between where it guards them from jumping from one to the other. All right, so that's the cool thing about orthogonal frequency division multiplexing. Okay, orthogonal. All right, and that's the one we use today. If you're using AC, this is what you're using. All right, and this is what you'll see if you have a spectrum analyzer. Okay, so OFDM is a technique for transmitting large amounts of data over a radio wave. Obviously, you have there WiMAX, 3G LTE, 802.11 AC, and higher. Right, and it's a 5 gigahertz technology. 5 gigahertz. Okay, that's where you're going to transmit at, and that's why they can go to where it says multiple smaller subsignals. Well, the SSS did that too, but they do it even greater. Right, the way they subdivide it into more signals, creating more phase shift keying, which was going to allow you to compress, which they did. They compress the signals, but they don't interfere with each other. You're 5 gigahertz. Not everybody transmits at 5 gigahertz. You're not going to be interfered with. So as of now, this is the latest and greatest type of modulation for wireless LANs. And this is the reason that Wi-Fi 6, all right, is so fast that they can get it at supposedly 10 gigabits per second. I haven't yet to see it because I haven't bought any Wi-Fi 6 equipment. All right. But I know with AC, I get close. I've gotten, I think maybe, I don't know, I'll be conservative here, like 700, a little bit over 700 megabits per second. So that's pretty damn close. I mean, if you can transmit at 700 megabits per second wirelessly, that's pretty damn good. Okay, but this is the type of modulation that is used because not only in a wireless network, not only are you going to look at the power that, remember we talked about the EIRP, the effective isotropic radiated power being transmitted because of the, you do that little calculation of gain and loss, the 310 rule, right? To see how much wattage is coming out, how powerful, and depending how powerful that signal gets sent out, it creates a carrier wave, a certain frequency. So you gotta be careful. You are dictated by the FCC how much power output you can put through an antenna, because if not, you can interfere with someone else's frequency. And we talked about that in the previous lecture. All right, but also the modulation type that we use, the intelligence, and how we're breaking up that carrier wave so we can put more intelligence, more data on it, so it can be a crisper signal. But now we're at the 5 gigahertz range where it can't go as far, okay? But definitely, I mean, this is not wide area network technology. We're not talking about wide area wireless, okay, networks where you're using, radio towers and satellites and all these different types of things, microwave and all that. We're talking about like 3G, okay? We're talking about where cellular. We're talking about LANs. Definitely, but it's still, OFDM is still used in these areas as well because of the type of phase shift keying that it is able to do. So know these terms for at least for your certification purposes. The terms of what is DSSS, or FHSS, frequency hopping spread spectrum. My God, I can't even talk anymore. I gotta look at it before I say it, because I'll mess it up. Direct sequence spread spectrum. Definitely know that, DSSS. Know that it takes the data, scrambles it up into particular bits, and then it creates a symbol depending on the modulation type. It'll create a 1 megabit data rate, a 2 megabit data rate, or a 5.5 megabit data rate, and then turns it into a particular symbol and puts all the information there. And then once it modulates it, it sends it out the antenna, creating a particular type of peaks, all right? So it can go ahead and not interfere, but look at the channel. It's 22 megahertz channel right here, okay? And then obviously we have the OFDM, which is what we use today. So know these terms. These are things that are important. And the higher the type of modulation you have, which right now it's OFDM, which is what Wi-Fi 6 uses as well, all right? Just know that it is directly related to these radio signals into smaller sub-signals. So the more sub-signals that you can create and the more you can compress the carrier wave and still keep them separate, all right, those waves, those peaks, right? Between peak and peak is at the phase. That's why it's phase shift keying between peaks of those carrier waves. Then you're going to get a lot more crisper. But again, even though it's more frequent, the signal is 5 gigahertz, but you can be able to put more intelligence on it because we're creating more carrier waves. They're not as close to each other. Nothing's going to interfere with them. So it's going to make it a lot better. But so you see, there's a lot of different things. You just can't say, well, I got a wireless router that can run. I got Wi-Fi 6 routers. I got Wi-Fi NIC cards. My laptop runs on Wi-Fi. My printer, you got all this stuff. Okay. Obviously, you're going to be using that type of modulation, but did you put it in the correct spot? Are your APs being interfered with anything? And if you're running Wi-Fi 6, I'm assuming you're running it at a business. Okay, this would be an overkill at a house, but hey, if you're a gamer, I can see. All right, but in a business is where in an office setting, in a real office setting, in a building, is where you would see maybe something like this that you would run. You need to be maybe very careful when you set up these routers and these APs at, especially if you're in hospitals or lawyer's office, architectural companies, surveying companies, all these different things you need to be careful with if you're doing things wirelessly, because a lot of data, when you talk about data, because it takes the data, breaks it up. Okay, a packet that's coming from, where's the thing that surveyors use? I forgot. That creates those, using plotters. Oh my God, I forgot what it was called. Okay. The whole thing is that the data they transmit is huge. It's humongous. It's a humongous thing. So remember, it needs to take that large chunk of data and break it up into different bits and then start sending it out. Okay, so it needs to break that up, and then on the other side, it needs to put it back together. All right, so think about that. All right, and that's why we have that overlap that we need, 15% overlap. Okay, so we can always have some sort of wireless connectivity. So that's why, again, so important. We use your spectrum analyzer to do the radio site survey, so you can put your APs at the correct spots. Because if you do have a large enterprise business, definitely you'll be doing things based on with wireless controllers that are connected to your routers. Then they're going to be sending out the information to the APs, and then the APs will send that out. You'll get APs going out to end devices. That will be the hierarchy that you'll set up. So you got to make sure that your APs are within that range. Another thing that that we'll talk about when we start talking about interference and antenna types is the transmission of power. Okay, you can control it if you have business grade equipment. If you do not, then you can't control the power. If you just buy something at Best Buy or something like that, or typical, wherever, Sears, I don't know. You buy, I'm showing my age. You buy a device like that, it's an all-in-one, it's for the home. You don't have really a lot of control over everything, okay? Especially the power. You can't control how much power output you have. That's why your neighbor can pick up your signal. That's why when you go to any hotel or you go to any neighborhood, you see everybody's SSID, the security set identifier, right? Now they've done, WPA2, and we'll talk about security as well. WPA2 personal, they put their little, password in, whatever. All right. And they're secure. They have a little lock. You can't get into it, right? Supposedly. But that's what you see. So that means it's being transmitted. You're so far away, you see these people's SSID. So if you can connect, if they don't secure it and you can connect to their SSID, now you got wireless. And how do I know this? Because this is what I used to show my students, okay? When we walk around. I said, look, here's an SSID. We're moving away from the school. We're in the middle of the parking lot, and we're picking up another business that's on the other side. We're picking up their SSID, not secured, and we were able to connect to it. And then they left all the default settings, and we can get inside their router and everything. We didn't do anything, but just goes to show you that even in a business, people are not taking the proper precautions to be able to secure their wireless networks. They don't do what they're supposed to do. Not only are you emitting outside your own building, this is a business. Your signal is going outside your own business. So somebody in the parking lot can receive it, or they can see you, and then on top of that, you're not going to secure it. Okay, well, you're asking to get hurt. You understand? So this is why we use this. So in a business setting, you can control a lot of these different things. In a home setting, it's very, very little that you can do. I mean, you can do a couple things, and I'll show you, like in a home setting, difference to a business setting. But if you're running to finish this off, in today's technology, anything less than 802.11 AC is ridiculous. If you're using less than that, you should be running at least AC. I mean, if I want to go, dirt bottom end, okay, but you should be using AC at least. I think in my brain, 802.11 AC, and then obviously secure that. All right, and make sure that everything, and in the 5 gigahertz range, not the 2.4. Why would you go 2.4 when I just showed you in this particular lecture, in the previous lecture, that in 2.4 you only have 3 channels. You're using DSSS, and here if you use 5 gigahertz, you can be using OFDM, which is a better type of modulation that's going to give you a crisper. You have more channels that they're not overlapping, and you have a crisper signal. Think about that. So that's modulation. That's modulation. Okay, it's the intelligence of that you're putting onto the carrier wave, but based on how the type of modulation is depending on how it puts that intelligence on there, and it takes that carrier wave, increases it, or it compresses it, puts it into more channels. It all depends on which one you're using. And obviously, anything less than DSSS, you're out of gas. OFDM now will be the one you need to be running. So check, check all that stuff. All right. I hope you understood all that. Go through the presentation. Take a look at the terminology. Make sure you know that for your shirts. But that's pretty much it. All right. I'll see everybody in the next one.